what I want to talk about are just some of the properties of canonical functions. And these, it's a good way to practice, like, for example, looking at increasing versus decreasing, looking at, for example, symmetries. So first off, let's take a look at this one. And we're going to focus on algebraic functions. These are functions that are sums and differences of polynomials. They're products and divisions of polynomials, or ratios of polynomials, quotients, excuse me. And then you can take roots of these as well. So let's take a look at some of these. So first off, f of x is equal to x. Now, what this looks like, this is what's called the identity function. And it slopes up here at a 45-degree angle, like so. Now, this function is always increasing. And so when we talk about increasing and decreasing, we're looking at how the function behaves as we go from left to right. So this is always increasing. Now, for its symmetry, if we plug in negative x, now we know that f of x equals x. That's what our function is. So if we plug in negative x, well, we get negative x, or negative the original f of x. Remember, if you take a look at x here, x is equal to f of x. There, we missed an equal sign. So what this tells us, it's symmetric about the origin. So for increasing in symmetry, that's what we have for f of x equals x. Now, let's take a look at the next common canonical function. F of x equals x squared. So this one looks like this. So as far as increasing and decreasing goes, as we go from left to right, it's actually decreasing at first until we get to x is 0. Zero there. And then with 0, it starts increasing. So it's always getting smaller here, then we hit 0. And then also starting at 0, it's always going to be increasing. It's going to be getting bigger. Now, as far as symmetry goes, our f of x is x squared. So if we put in a negative x, so we square the negative with x, we get x squared. And this is just the same as f of x. So what this tells us is that any point that's on the graph here is directly across on the graph over here. This is symmetric around the y-axis. Now, the next canonical graph is x cubed. Oh, sorry, thinking of x to the 1/3. Now, this function is always increasing. So as you go left to right, it's increasing, increasing, and then it starts to actually level off. And then it starts increasing again. So the rate of increasing slows down near the origin, but then it picks up again. So it's increasing everywhere. Now, for its symmetry, so if we plug in negative x, because remember, x cubed by itself is f of x. So this means when the minus sign pulls through like this is symmetric about the origin. So we've looked at f of x as x, x squared, and x cubed. Let's look at some negative exponents. So this function, this is a rational function. It looks roughly like this. And then we have a vertical asymptote coming down the middle. And the reason that's there is that when x is 0, you get division by 0. Whenever you get division by 0, you get the vertical asymptote. Now, this is a boundary our graph cannot cross. Now, there are such a thing called, for example, a horizontal asymptote, and those your function can cross. That's okay. So let's take a look at this thing. What is it doing? Well, as we move along this branch, it's always decreasing. So as long as we're on this graph, we're getting smaller and smaller and smaller. And the graph is undefined at x is 0. So it's decreasing here. We're undefined at 0, so we don't ask that question. As we follow this branch, it's also always decreasing. As you go left to right on this branch, it's always getting smaller. So this thing is actually always decreasing. So it's decreasing on its domain. Now, the domain here is negative infinity to just short of 0. And then if you're sitting on this branch, as you go from left to right, you're also always going to be sliding down the graph like that. Now, what about symmetry? So this one here, you put in negative x, the negative is going to come on through. So this means we're symmetric about the origin. So that's f of x equals 1 over x. Well, let's take a look at another one. Let's say f of x is 1 over x squared. Well, what this one looks like something roughly like this. Now, in this case, though, if we look at the two branches, on this branch, we're always increasing. Now, I should note, we also have a vertical asymptote at x equals 0. If x is 0, we'll get a division by 0 squared, which is 0. So this is increasing. And then it's also decreasing. On this branch, it's dropping down. So here we got a function that's doing both of these, just like x squared, f of x equals x squared. Now for symmetry, what we've got is we put in negative x, and then we just get f of x that results out of it. So that means this is symmetric across the y-axis. And you can see it. It's a mirror reflection of itself across the y-axis. So let's take a look at some roots. This is the square root of x, or x to the 1/2. And it's going to look roughly like this. So because we have an even root, what that means is we can't take an even root of negative numbers. And we can express that using the fraction 1 over 2. If you want, you can imagine a 2 in here like that to give you a square root. The key thing with this, again, we do see its domain. It's limited. Now, this is really we've seen some limits on domain already. When we had 1 over x and 1 over x squared, we had vertical asymptotes at x equals 0. So 0 was not part of the domain of those graphs. This one here, the domain, because we can't take the square root of negative numbers, it's only 0 and the positive numbers, and that's it, no negatives. So for increasing and decreasing, this function is always increasing. Again, as we go from left to right, it's always getting higher and higher. And then that's going to be it. So as far as symmetry goes on this one, well, you can try to do a test, but you're going to run into a problem. Remember that x is greater than or equal to 0. So that means negative x is less than or equal to 0. So we're trying to take the square root of negative x. That's not going to work. So this test won't work. Another thing you can look at when you think about symmetry, across the y-axis, we would see a mirror reflection like this, but we don't see that here. So it's not symmetric across the y-axis. If it's symmetric across the x-axis, we would see a mirror reflection here. Well, we don't. We just have this. So it's not symmetric across the x-axis. And if it was, it wouldn't be a function. If it's symmetric across the origin, if you have, say, x and y here, well, then you're also going to have negative x and negative y in here. But we don't have that. We just have this thing right here. So this has no symmetry. So that's the square root of x, or x to the 1/2. Now let's take another look at another canonical root graph, x to the 1/3. So this is x to the 1/3. It looks roughly like this. Now, this function is always increasing also. As you go along here, it's getting bigger and bigger and bigger and bigger, and it's just going to keep being bigger, bigger, and bigger. And as far as symmetry goes, and when you take the cube root of a negative number, your answer is still going to be negative. So the negative just pops out, and then we just have to figure out x to the 1/3. You can try this. The cube root of -8 is -2, while the cube root of 8 is +2. So what this is negative f of x. So f of negative x gives you negative f of x. So what this means is we have symmetry across the origin. So it means a point here is also going to be found down here. So as far as canonicals go in terms of algebraic functions, there's two others that they have in the text that I do want to show you. And they do have to do with roots and powers. And so this one, again, what we've got a 2 here in the denominator. So that means we're actually taking a square root of some kind. So that means we're either dealing with the square root of x and then we're cubing it, or we're dealing with x cubed and we're square rooting it. Now, here, I'll draw what this looks like. It looks roughly like this. And again, you can see, just like with the square root function, it doesn't have any negatives. You can put 0 in here, that's fine, but no negative values because, well, here's the thing. Take the square root of a negative, can't do it. If you cube a negative, you're also going to get a negative. Negative 2 cubed is negative 8. And then you're going to take the square root of a negative. Now, it might have been a while, but you might be wondering, how is this leading to that? Well, here's the deal. We could think of this as x to the 1/2 times 3, or 3 over 1. And so we can rewrite this as x to the 1/2 to the 3rd power. When you have exponents like this on the outside, you multiply them together. So that means we'll have the square root of x cubed. So that's one way of going about this. The other way well, multiplication's commutative, so the order doesn't matter. So we could have this 3 times 1/2 instead of 1/2 times 3. So then we have x cubed to the 1/2. Again, it's an exponent outside parentheses like this. These get multiplied together. It's a rule of exponents. So what we get is x cubed square root. Either way, what this is saying is if we take a negative number and we cube it, we get a negative number, and then we have to square root that, which we can't do. Or we're going to try to square root a negative number right away, and that's something we don't want to be doing. So this one, no negative numbers. So is this increasing? Yeah, it's always increasing. As you go left to right, it's always getting bigger. And as far as symmetry goes, this one, again, you can try to put in that negative x. And we could say go with this version of it. Now remember, our domain is we're always using 0 and positive numbers. So if we attach a minus sign to 0 or positive numbers, well, if it's 0, it's no big deal. But if we're doing the positive numbers, we're going to be taking the square root of a negative. It's not going to work. And again, we can look at this. If it's symmetric across the y-axis, we would see something like this to go with it. But we don't. We just have this. So there is no symmetry across the y-axis. If it's symmetric across the x-axis, we would expect to see something like this to go with this, but we don't. And if we did see this, it wouldn't be a function anymore. It would fail the vertical line test. You'd be intersecting this at more than one point. But there is no second branch. This is not there. Finally, if this was symmetric about the origin, if you have xy, you would also have negative x, negative y. So we need to see something like this. And we don't. We just have this. So this tells us there's no symmetry. at least no symmetry with regard to, say, x-axis, y-axis in the origin. So, all right. So that's that function. That's sort of a, not always a very common one. Now, another one, though, that they have in the text. Now, this one, because even though it's still a fraction, we still have an odd number in the denominator. That means we're taking a cube root, and so that means it's okay to use negative numbers. Again, we can think of this as we could think of it like this. So in this case, if we let x be negative, we're going to square x, and the negative is going to go away. But I mean, even if it didn't, you're taking a cube root, and so cube roots can handle negative numbers. Or we can think of it like this. We could think of it like that, where we take the cube root first, and that's okay. If x is negative, that's not a problem. If it's positive, it's not a problem. And then whatever comes out of this, we square it. So this means that since there's no divisions by 0 here, this will have a domain that's the entire x-axis. So what this one looks like. Maybe this. Now, for this one, on this side of the graph, it's decreasing. As you go left to right, you're dropping in value along the y-axis. So it's decreasing on negative infinity and 0. And then, again, starting at 0, you're always increasing, getting higher along the y-axis as you go left to right. So you're increasing on 0 to infinity. So finally, symmetry. Put in negative x. And what we could do, we could use the version of this that was the cube root of x squared, except now we're replacing x with negative x. We can use this version of it. And clearly we're squaring this, so that's going to get rid of the negative. You take negative x and you square the whole thing, you just get x squared. Negative x times negative x, the two negatives become a positive. X times x is x squared. And so this is just that x to the 2/3, or f of x. So f of negative x gave us f of x. This means we're symmetric across the y-axis. All right. So there's one more canonical function I want to show you. It's a piecewise function. And with this piecewise function, what it's going to look like is something like this. Now here, it's decreasing on this side of 0. So negative infinity to 0. And then from here, starting at 0, it's going to be increasing. So what about symmetry? Well, let's take a look. Well, if we put in negative x, so what this is going to do right away, you can treat this actually as -1 times x, or the absolute value of -1 times the absolute value of x. And then finally, that's just going to leave you 1 times the absolute value of x, or the absolute value of x, which is f of x. So what we have here is symmetry across the y-axis. So this little trick here I did with the numbers, again, it might have been a while since you've done this, but it's a trick with absolute values. Absolute value of c times some function of x. And c is some kind of constant. It's equal to the absolute value of c times the absolute value of f of x. All right, so that's just a review of the canonical functions. If you have any questions, let me know, and have a wonderful day.